Okay.
Next, if it works for you, I think, yeah,
Okay.
perfect. Sure.
Yeah, good evening, everyone. So in this session, I am going to be talk about building distributed systems using an event-driven and streaming architecture with the NATS JetStream. So let me introduce myself. My name is Shiju Varghese. I'm basically a solutions architect focused on distributed systems. I am currently working as a consulting architect, not part of any one company. I provide consulting to various organizations and providing training and consulting on Go programming language and distributed systems architecture. I'm a published author of 2 books on Go programming language. So before embracing Go as my primary programming language, I worked extensively on Microsoft technologies and awarded Microsoft Most Valuable Professional for 7 times. And I'm a regular speaker at many developer conferences happening in India. All right. So this is the agenda of this talk. First, I will give a brief introduction about what is an event-driven architecture. How can we leverage event-driven architecture with the streaming architectures? Then I will provide a brief introduction about NATS JetStream for how can we leverage those kind of architecture for building your distributed systems. Finally, we walk through some source code with the Go programming language because I primarily work on Go. So we walk through on some source code how to build such kind of distributed systems. All right. So before going to JetStream directly, so let's have a quick look at what is the event-driven architecture, what is streaming architecture. Then we will look at how can we leverage JetStream for building distributed systems by using such kind of architecture. Okay. First, let's have a look at what is the event-driven architecture. So when you build distributed systems, especially a microservices-based distributed system, we often use an event-driven architecture to solve many practical challenges associated with it. Especially when you build microservices-based systems, there are a lot of practical challenges are there. It is not easy to build a microservices-based system. A lot of people saying that microservices is just using container. That is wrong. But when you build a real-world microservices, you may come with a lot of challenges. In a microservices-based architecture, you take a large domain model and divide into several subdomain, because the idea of microservices architecture is all about functional decomposition. So you take a large domain model and divide into several subdomain model. We call it a bounded context in domain-driven design concepts. And we build autonomous microservices for each subdomain. And eventually, you may end with each microservices use its own database. That will start a lot of complexity because your data is scattered into different database owned by individual microservices. So the challenge is when you make some business transaction, let's say you build an e-commerce system by using a microservices-based architecture. Let's say there is a order microservices. When you place an order, this order microservices might be taking the request. It does something. It does something on its database, and some other actions might be performed by other microservices. So many transactions may span into several microservices. Then you may need to talk with the different databases where how can we perform distributed transaction? That is a big challenge. And another challenge is because this data is scattered into several databases owned by individual microservices, how to query the data? How can we perform an inner join? Because data is scattered. Order is in one database, customer in another database. How to perform this joining? So these kind of things are a big challenge. So these kind of problems can be solved by using some kind of an event-driven architecture. A lot of people are using an event-driven architecture approach called event sourcing. And event sourcing is again used with another architecture called CQRS. So along with event sourcing and CQRS, you can solve some practical challenges, but it brings new kind of problems. The complexity problem. We can solve all of these problems because things are distributed, our business logic is distributed, our application data is scattered into different databases and everything. So many of these problems can be solved by using an event-driven architecture. So in an event-driven architecture, an application is composed of independent components that react to events published by other components. In a microservices architecture, some microservices publish some events. Let's say order has been placed. So to let other microservices know that, it simply publish by using some distributed messaging or a distributed streaming system. So other microservices which are interested to know that, yeah, a new order has been created, can simply subscribe those messages, and it can do its own actions and again publish other set of events. So that events might be interested by others components of your distributed system or your microservices. Those system can process the data, does something, and again publish other set of events which might be subscribed by again other components in your distributed systems architecture. So here these events are some facts happened in your system. Let's say order has been placed, payment transaction has been completed, order has been approved, order has been rejected. So these are some facts happened in your system. These facts are immutable. They cannot be changed or be retracted. If you would like to change your application state, then again, you need to publish some event. And an event is part of flow of information, and composition of events makes application state. So integration logic and transaction logic are pushed to producers and consumers of your distributed messaging or a distributed streaming systems. That is all about event-driven architecture. So in a nutshell, just have a quick look into this simple scenario. Let's say there is a order microservices. When you place an order microservices take that request, it does something, it may do some transaction on its database, and to let other microservices know that a new order has been placed, it can publish events to a messaging infrastructure. So let's say there is a other service called payment service, which can subscribe those messages and it can complete the payment transaction and again publish other events. So let's say there is might be a review service. This review service can subscribe those information and do something from that system. So that is basically an event-driven approach. Then let's have a look on what is actually event streaming. So event streaming involves a continuous flow of data from various sources, like components of distributed systems, like a microservices-based systems. Lot of individual microservices are participating in completing your business transaction. So you collect, you ingest a continuous flow of data from various systems and from IoT sensors, edge, software application, and databases. And these streaming data containing information about an event. For example, in a microservices architecture, all of these domain event, a order has been created, order has been approved, or a change in your application state. And this streaming data typically processed in real time, even though although the type of the data and the nature of event may make the resulting action, but typically we process this streaming data in a real time by using some streaming processors. So then what is distributed streaming system? Typically people think that both messaging system and streaming systems are almost the same. The reason is there is a publish subscribe is there. Even if you look into the Kafka developer community, a lot of people, I'm not talking all people are not in the same league, but a lot of people think that it is like a messaging system, even though they use a distributed streaming system. So there is a big difference, at least from a technical perspective, architecture perspective, there is a big difference between a messaging system and streaming system. So in a streaming system, it captures data streaming from various sources, components of your distributed systems, IoT sensors, edge devices, various software application databases, and these data streams persist into persistent store. So you persisted, data is there. Now you can replay the messages. For retrieval, doing some processing by using some stream processors, or taking this message, a stream of messages, to build an event-driven architecture in like a microservices based distributed system. So that is the fundamental idea of distributed streaming system. If you look at a distributed messaging system, when a developer writes the code, same, publish, subscribe, publish, subscribe, there is no difference. But the entire architecture is different. In distributed messaging system, the emphasis is into buffer the message at a messaging server. When publisher system publish the messages, then simply forward those messages into a subscriber system or a consumer system. When a developer writes the code, there is no fundamental difference. But architecture perspective, there is a huge difference between a distributed messaging and distributed streaming systems. Yeah, now let's have a look at what is NATS JetStream. So NATS JetStream is a distributed streaming system, not a messaging system. So which means that persist streaming data and replay or consume messages by using consumers or subscriber systems. So enables temporal decoupling between publishers and subscribers. It means that if you use a conventional messaging system, when you publish the messages, in order to get those messages, in order to subscribe those messages, subscriber system should be active at the same time. Let's say some subscriber system is down because of a network failure or due to some different reasons, subscriber system is not available. Then those systems will not receive messages. You lost the messages because there is no persistent store. There is no replay mechanism. It's simply buffer and forward. So here, persist in a persistent store and replay for retrieval, the stream processing. So there is a big difference between both approaches. So when come to Jetstream, it enables temporal decoupling between publishers and subscribers. So when you publish the messages from various publisher systems, your subscriber system should not be active at the same time. Let's say some systems are down, no problem. Let's say some subscriber system is down due to a network failure. So whenever it is active, it can start from where it stops. So it enables a truly an asynchronous communication without the need of both publisher systems should active at the same time. So Jetstream provides a temporal decoupling between publisher systems and subscriber systems. And another thing is Jetstream provides exactly one semantics for the delivery of messages. The reason is, so there is a persistent stories there. So you can easily replay the messages. At the same time, Jetstream or any kind of distributed streaming system provide very powerful acknowledgement mechanism, which lets the consumer systems to acknowledge the messages to the server infrastructure to let know that these messages are received. So there is a persistent store is there. there is a acknowledgement mechanism is there. So it provides at least once semantics, but Jetstream can provide exactly one semantics. It can avoid the duplication of receiving the message from subscriber system. So it actually provides exactly one semantics for the delivery of messages. And very interestingly, Jetstream bundled in with the core NATS server. You can use the same NATS server executable for running your Jetstream infrastructure as well as your core NATS server. And you can easily enable and disable. So before Jetstream, there was a service called NATS Streaming Server. Some of you heard about NATS Streaming Server, for which we use a separate executable. At the same time, we were using a separate client SDK. So now the same executable for running your server infrastructure, you can easily enable and disable. At the same time, you can use the same client SDK. So it is very easy. And as the previous talk, in the previous talk mentioned, NATS uses a wrapped consensus algorithm for distribute the persistent service between the NATS server in a cluster. So because of all of these capabilities, a powerful streaming infrastructure that comes with the better acknowledgement mechanism and everything, by leveraging this kind of capabilities, we can build next generation of event-driven streaming systems when you build modern distributed systems. Okay, so now let's look at some basic things of Jetstream. Then I will show some piece of source code in order to work with the Jetstream infrastructure. So the first thing about this Jetstream is the streams. So streams are basically message stores. Streams are basically message stores that persist into persistence infrastructure of Jetstream. So where many related subjects are stored into one stream. For an example, let's say there is a order stream, a one stream. Then you produce and consume stream of messages to and from this stream with a related subject, such as, let's say, order is placed, orders dot placed, orders dot approved, orders dot payment debited, orders dot rejected, orders dot delivered, orders dot shipped. So all of these related subject can be associated with the one store. So whenever you publish a message on orders dot created or orders dot approved or orders dot rejected, so those messages will be stored into order stream. And for other related things, you can create a different stream. So streams are simply message stores in Jetstream infrastructure. All of the related subjects belong to a single stream. Then consumers. So consumers are a views on a stream because we persist all of these messages into a stream, which is a message store of the Jetstream infrastructure. And these consumers are a views on stream, a subset of stream. So you consume by providing a delivery subject. You say that, yeah, just subscribe messages on orders dot created, orders dot payment debited, orders dot approved. So you consume these messages from the stream, which is persisted into our persistent storage mechanism. And yeah, so as we mentioned, consumers can provide at least once delivery guarantee, which is not available in a conventional messaging systems. And consumers are not one type. So before Jetstream, subscribers were simply push-based subscriber. Server is whenever publish the messages on the messaging infrastructure, server simply pushing the messages to subscriber system. So you receive the message early as possible. But when it comes to Jetstream, Along with the conventional push-based consumer approach, they are also providing a pull-based subscriber, which is very efficient. With a pull-based consumers, client application can request a batches of messages on a specified delivery subject on demand. So client is getting more freedom. So the benefit is when you build highly scalable distributed systems, horizontally, you can pull the messages. So that is very efficient. So in my opinion, pull-based consumers can get the same benefit of a push-based consumer, even though infrastructure is a bit different. From a practical perspective, both are almost the same. At the same time, you will get some extra capabilities. Horizontally, you can easily scale those kind of consumer system if you could use pull-based consumers. And as the previous talk mentioned, consumers can also be ephemeral or durable. So if you want to, let's say, once some subscriber system inactive, then whenever it's active, if you want to start the messages from where it stops, it should be a durable subscriber. So when you create a consumer system, you should provide a durable name. Then it will be a durable subscription. What happened? Okay. So as we discussed earlier, we can use the NATS server executable for running the basic NATS server and the JetStream server. So we use the same exe, NATS-server. If you provide a JS flag, JS stands for JetStream. So NATS server run as a JetStream server that comes with the persistence for your stream of messages. Or you can also start with some configuration file. Just enable JetStream in your configuration file. Okay, so now let's have a quick look into some source code in order to understand how to make this publish and subscribe. So I'm primarily working on Go programming language. So the code is written in Go as well. So if you are using Go programming language, these are the Go client SDK I have used. So there is a nats.go package is there. And very recently, this package also providing a sub package in order to working with the Jetstream. Earlier, the same package was using for working with the basic NATS server as well as the Jetstream server. With the new sub package with the name Jetstream provides a better API in order to working with the Jetstream. Okay, then the source code is available in my GitHub repository. So in this full-fledged demo, as I mentioned, which is written in Go programming language, I use NATS JetStream. Along with the NATS JetStream, I am using one more NATS service called NATS Micro. NATS Micro is a services framework come from the NATS ecosystem, which can be used for building a RPC style services. It might be, I believe that really good for the edge. So you can create small services by using this NATS Micro framework. Okay, first we will look at how to create a stream. So you can create stream by using a CLI tool, by using various admin tool, and you can also create stream in a programmatic manner as well. So this is a code block which I have written in Go programming language. So the API is, if you are already working on Go, even though you don't work on Go, this code is very readable, not a big deal. The beauty of the NATS ecosystem is the entire ecosystem is very simple. And when it comes to programming as well, the API is very simple, very straightforward. So here, if you look into the code, yeah, we just create a NATS connection. Then once you create a NATS connection, you can create a JetStream instance with a NATS connection. Then just create the from the JetStream instance, there is a API. There is a create stream API is there. Also create or update stream is there. So, and you can configure all of the things. So here I am specifying the name of the stream is orders, and the associated subjects are orders.star, which means that all of the message published on subjects like orders.created, orders.payment debited, orders.approved will be persistent to orders stream. Very simple, very straightforward. So we created a stream. Then let's have a look at how to publish messages. It's very simple, very straightforward. So once we create the JetStream instance, it provides a publish API as well as publish MSG API. So in this code block, I am using a publish MSG API. I am providing data that representing some order, and subject is orders.created. The subject is orders.created. So whenever a new order is placing, from the order microservices, we simply publish the messages on a subject called orders.created. So that orders.created is part of a order stream. So this data will be persisted into our order stream. Then let's have a look at how to create consumer systems and pulling the messages from stream and being reactive to events of data streaming. As I mentioned, there are two kinds of subscribers are there: push-based subscriber and pull-based subscriber. When you use the new Jetstream package, you always create a pull-based subscriber. If you use the old package, NATS.Go main package, you can create push-based subscriber system. As I mentioned earlier, pull-based subscriber system can provide the same benefits of push-based subscriber, plus you will get some extra benefits. You can easily horizontally scale your pull-based consumer systems. So again, we create a Jetstream instance here. Then there is a create consumer is there, or create or update consumer is there. Then by calling this create or update consumer, we create a consumer system. So here we provided a durable name so that it will be a durable subscriber. So when this subscriber is down, whenever it reactivate, so we can receive the message from where it stops in the previous state. Then we provide the subject by providing a filter subjects property of our consumer configuration. So it creates simply a consumer. We simply create a consumer. Once we create a consumer, we fetch the messages by providing a batch number. Let's say just pull the 10,000 messages, process it, just take the next 10,000 messages. And by horizontally scaling your pull-based consumer system, it will be very efficient. So then the next code block, we are fetching the messages by providing a batch number. Then we subscribe all of this message and we acknowledge the messages. One powerful system of any kind of streaming infrastructure is there is a acknowledgement mechanism. The consumer system can acknowledge the message to the server infrastructure whenever you receive the messages. You can configure in a manual acknowledgement, you can configure implicit acknowledgement and everything. So here we manually acknowledge to the server infrastructure. And once you subscribe this message, because this message contains information about, let's say, about some event, a new order has been created. A new order has been created. So let's say this is a payment microservices which does all of the payment transaction. So it can do its own job. its own actions. Then again, it can publish other event. Say that, yeah, this payment transaction has been completed. So this event might be interested for some other microservices or other component in your distributed systems infrastructure. So we subscribe the message, we do something, then again we publish other event. So there is in our earlier code block, there was a publisher. Whenever we create a new order, then there is a consumer. Consumer subscribe those messages. It does some actions, might be a payment transaction. Once it completes, it publish other event to let other system know that, yeah, a new domain event has been created here. So do something from your side. So again, from the same system, after we do some action, we publish other event. Let's say payment debited event of your order, orders.payment debited. So we publish other event. So this will be interested for other systems. So in a microservices architecture, when you perform many business transactions, it may span into several microservices, not easy. A lot of people say that microservices is just running in a Docker container and clustering with the Kubernetes, just done. It's not that much easy. It's a distributed systems architecture, not about running in a container. That narrative is wrong. And it is not good to associate an architecture with some tools. Even let's say I am saying that I am using JetStream. Now this is my microservices. That's a wrong narrative. We don't need to tie it up with any tools. So what I'm saying is building a distributed system is not easy. It's very painful. At the same time, it is really exciting. If it is painful, means that it is really exciting. Yeah, so when this payment transaction event is happening, again, we publish some event, then there is another system that subscribe, that consume these messages and do its own actions. Let's say it's a review service, finally approve the order or do some order processing by receiving messages from stream. And again, we do publish other event. We change the order status, approved or rejected. So we publish another event. A lot of events are happening. Sometimes a single transaction may span into several microservices or several components in a distributed systems architecture. So that many people eventually end with a event-driven architecture called event sourcing. In event sourcing, you persist event information. You persist events, domain events, and associated event data. Then again, you typically use this architecture with the CQRS architecture. There is a separate model for write operation, separate model for read operation. Write operation for your domain events, persistence on your domain events and associated data. Then you will have a separate read model. Read model take the data from the write model and you create a queryable data model. So things are not easy, but it is interesting, exciting, painful. Okay, so this is fundamentally event-driven architecture, along with the streaming architecture. The benefit of streaming architecture is, as we discussed earlier, we persist all of these stream of messages so that we can easily replay. So these messages containing some information about the event, might be some state change of your application. So everything is persisted. Let's say you are adding a new system after some time. Even if you want to get historical data for doing something, it is possible with a streaming infrastructure because everything is persisted. And you don't need to persist forever. You can have a retention policy. Otherwise, it will be very big. The storage will be very big. So you can have your own retention policy and everything. So in that way, you can solve many practical challenges associated with a distributed systems architecture, especially with a microservices-based distributed systems architecture. And Jetstream is very simple system. There's no complexity. There is no too much complexity, even for infrastructure people, as compared with some other technologies. And for developers, it is very simple, very straightforward. So that is all about Jetstream in a nutshell, and how can we use such kind of architecture for building modern distributed systems and microservices-based distributed systems by combining the power of everything, event-driven architecture, event streaming, and Jetstream enables all of these things. Yeah, that's about.
Thank you so much, Shiju. So, anyone in the audience has any doubts?
And you can, so there is a supporting downloadable source code is there in GitHub. So you can take the source code, just have a look into the entire workflow.
I have two questions actually. So the first question is, in one of the slides, you said that it supports exactly once message delivery semantic, right?
Yeah.
But in another one, you said that the consumers support at least once delivery, right? So could you make it more explicit as to which one? Or
yeah, at least once means, see, in a messaging system, the delivery model is at most once. At most once means it simply forward the message. There is no guarantee. There is no guarantee. At most once means buffer the message at server and simply forward to all the subscriber system without a guarantee. There is no acknowledgement mechanism. There is no acknowledgement mechanism. At the same time, there is no persistent storage. It's simply forwarded. So that model is known as at most once. At least once means your subscriber system will receive the message at least once. And exactly once means that there is a chance to have a duplication of messages. Jetstream can avoid that situation by associating with a unique publication ID. Publication ID, it can solve that problem of having a duplication of messages from consumer system. In sometimes, in some infrastructure, there is a chance to get the same message again. But in Jetstream, in the message header, it will include a publication ID, and it can solve the problem of duplication of getting messages along with the at least once. That means exactly once. Exactly once means there is no duplication of messages.
okay, the second part of my question is, of in a slide you showed the whole workflow, right? That means there is this order and you debit and all of this. So for cases like this, isn't a workflow system a better option, or why would someone choose maybe NATS or Jetstream over a workflow system? By workflow system, I mean stuff like conductor, temporal, airflow, and stuff like this.
Sorry, can you please repeat it?
So my question is, in cases where there is complex basically workflows, where let's take maybe an Amazon where I first place an order, then it's in my catalog, then I have to go to payments. That is a workflow, right?
Yeah, there is a lot of events are happening.
Correct. So in such cases, isn't it not better to use a workflow orchestration system rather than use something like a Jetstream or NATS or a queuing system?
See, here the underlying thing is there should be an event-driven architecture, because these components in a distributed infrastructure is, let's say there is a order microservices, there is a payment microservices, let's say there is a review microservices. All of these systems need to communicate to each other in a asynchronous manner, not in a synchronous manner. If you want to communicate in a synchronous manner, you should use some RPC style communication. That is okay for some kind of system, but if there is a complex business transaction is there, for an example, when it comes to a microservices architecture, the idea is functional decomposition. Functional decomposition means you take a big domain model that divide into several subdomains. Then for each subdomain, you create a microservices, which is also using its own database, so that your data is also scattered with a different database owned by individual microservices. So it is a distributed transaction. So you need to communicate with each system. You need a communication mechanism. One option is use the RPC style communication. You can use technologies like gRPC or any similar kind of RPC mechanism for communicate. It's a synchronous communication. From order, you call a payment microservices, then you call some other microservices in a synchronous manner when you do with the RPC style communication. Here, if the transaction is very complex, the RPC style communication doesn't work. So you need to do this in a event-driven manner. So where different systems can publish messages to let other systems know that, yeah, this domain event has been happened in our system, or there is a state change in our application data. So we need to do something. And when you do these kind of things, you also need an orchestrator sometimes. In a microservices, we call it a saga. Saga coordinates everything. But again, you need this event-driven architecture. So there is only two options. Go with the communicate over APIs. Again, comes to API, I highly recommend RPC style communication. RPC style communication is okay for some kind of systems. For example, at Google infrastructure, they typically use RPC. For everything at Google, it's simply an RPC by using their own internal RPC framework called StubB. Actually, gRPC is an open source version of the StubB framework. That is the one option. Another option is communicate asynchronously. And when you do this kind of event-driven architecture, you may also need some kind of orchestrator. Let's say when you perform a transaction, it may span into 5 microservices or 5 component distributed systems. 3 things are successful, everything is happy, but while performing something on the 4th system, it's failed. How to do all of these things, right? So for some kind of architecture, again, you need a kind of an orchestrator on the top of all of these event-driven approach. Some people uses an architecture called event sourcing. Event sourcing is your persistence model is completely unconventional. You don't follow any relational database. So you simply persist events information. Yeah, order is not created. This is associated data. Yeah, order is approved. This is associated data. This is like a version control system. In version control system, every commit is a new version. So this history is there. That is the one approach. So when you go with that approach, your write model is not a queryable data. Then you eventually go with another architecture called CQRS. CQRS is command query responsibility segregation. Then you use a separate model for write, that is your event store. Then for your query model, you can create a queryable data model. Where the benefit is, because there is a separate model is there, the technical data is there in your event store. You can retrieve the data, you can process, and you can create a queryable data where you don't need to worry about following a normalization. And sometimes it will very beneficial to quickly provide the queryable data, because you don't need to follow normalization. Even you can violate all of these theories, just provide data for your view. But again, there is a complexity. In software architecture, there is no perfect solution. Someone else says that, yeah, this is the best architecture. That is wrong. People do it, their marketing. Let's say someone else is providing a new product. They will say that, yeah, there is a serverless, a single solution for everything. Do it. And now people are using serverless for building REST API, everything. It's wrong. So there is no perfect solution. So when you run a business, you should market, you should sell. And if I am working in a company, I should use my common sense. to understand whether this architecture fits for my organization. Even for microservices, most of the organization don't need. Just for the sake of getting this name, this label, people use it. Labels don't make any sense. You can call your architecture ABCD, XYZ, Nutanix microservices. No problem. It should solve the problem. So there is no perfect solution. If streaming architecture is event-driven streaming architecture may not be suitable for some kind of system. There are a lot of things are there. Event-driven thing is there. Some system publishing, other system subscribing, again do something, again publishing, other system again subscribing. It's not easy. So there is no perfect solution. So the only thing we can do is don't become a poster child of others' intellectual thoughts, others' label. Microservices, serverless, ABCD, XYZ. Solve your problem and give your own name. Customers don't look whether you use event-driven streaming architecture. If it is working, that's good. I always tell my clients that go with a middle ground solution rather than becoming a poster child. Just put this poster on my shirt. It doesn't make any sense. So there is no perfect solution. So you understand this is the problem statement. Then what is the solution? There again, there is no perfect solution. So when I am talking about, just go with an event-driven streaming architecture for solving these challenges, it brings new kind of problem. Not the solution for everything, right? So there are a lot of things are there. So there is no perfect solution.
Sure, yeah. Thank you so much.
Any other questions?
So actually, to add to what Shiju said, so workflow systems, I think there's a defined point A and point B, and you need to go from A to B from using steps which are predefined. Event driven is more like ripple effects. So you have many side effects. So how do you cater to that? So for example, you hit service 1, there is a side effect that needs to now take place on S2, which is service 2. Then from S2, something needs to happen at S3, which is like you're creating ripples, right, in the system. So
and
that
again,
is event-driven.
let's say you focus on consistency. You should get real-time data. Then you don't get. So a lot of events are happening, right? Finally, you compose your application state. Then by leveraging all of these events and the associated data. The application set is composition of events. So if your requirement is you should get a real-time data, you don't want to work with the stale data. So your system says that getting real-time data is super important. You cannot go with such kind of architecture. There's no consistency. Here the emphasis is into availability. You work on stale data. Stale data doesn't mean that very old data. There is no guarantee of getting the real-time data because it's completely an event-driven. So a lot of things are participating to building such kind of complex systems. So you don't get real-time data. Theoretically, we can call it stale data. Stale doesn't mean that a long old, might be a few minutes. But that is very critical. So you should understand what is your requirement. Don't blindly adopt anything. All right. Thanks to everyone.